Man, I'm gonna be honest. This video has been very frustrating to make. This is already the fourth, I think. It depends on how you count it. The fourth iteration of me trying to record it and explain everything, and for various reasons, technical and not technical, multiple previous attempts were broken, so I'm gonna be saying the same things for the fourth time. And I'm gonna try to cut it as short as possible. But basically, here's the thing. I did a lot of things about division. Last time we solved division with a naive algorithm, and I had a few thoughts about it. And between then and now, I have implemented every thought I've ever had about it. So that's gonna be one part. And the second part is having built some of the things for which were necessary or useful for division, I got a lot of new ideas for how to improve other components. And that also happened, and I also need to explain that. So let's jump into it. So again, last time we solved division with a naive algorithm. Just to remind you, what we do is we have a numerator, and we loop forever, or well, we subtract from the numerator, we subtract the denominator from the numerator as many times as we can, and how many times we subtract is going to be our quotient. Now, in order to know when I need to stop looping, what I used to do is I kept track of remainder and remainder previous, so the previous result of subtraction and my current result of subtraction, and I was testing for overflow, right, in order to know that I cannot subtract anymore. So this is the first comment I want to make. In the comment section of the last video, Christopher rightly pointed out that that algorithm was way too convoluted, and actually this remainder and remainder previous is kind of not particularly space efficient, right? It uses more registers than necessary. In fact, I do not need to test for overflow, and this algorithm can be simplified by simply checking whether my remainder has gotten smaller than the denominator, right? This means that I cannot subtract anymore, but I have not yet overflowed, right? So this is essentially the same thing, except it uses fewer registers and doesn't do some unnecessary checks. So that's cool, and it works. But that's just the tip of the iceberg. Next up is, I'll just jump into the explanation of the algorithm I did. In the previous iterations of this, I used to have all sorts of formulas and explanations and properties of division, which really led to this mathematically and an explanation of long division. But long story short, right here it should be, yes. I implemented a much more efficient algorithm for division, which is based on the idea of long division, kind of. So let's just try to go through what's happening here. Hopefully it will be understandable. So just like before, we still have our remainder denominator. I did need the denominator previous. We'll talk about that. We also have our quotient, but a new addition is a thing I called magnitude. So let's take a look at the prep step. I don't know. It's just... hopefully I can explain it without all the formulas. So what's happening in the prep step? Man, I cannot explain this without the formulas. I don't believe it will make much sense. It's so difficult. So the idea of this algorithm, let's try it this way. The idea of this algorithm is essentially the same as the original div mod, except in the original, we are subtracting the denominator once at each iteration. And this is horrible, right? When we need to divide 255 by 1, we're going to be subtracting 1 to 55 times, right? But this is not necessary, right? If we were able to subtract 1 times 100 from the 255, then we would already know that 1 fit 100 times into 55, right? And it's the same idea. Except instead of doing 100 iterations, we just do subtract 1 times 100, and we add 100 to our quotient, right? So that's kind of going to be the idea behind long division. And in order to know how large a number I'm trying to subtract, I use what I call magnitude shifts. And what magnitude shifts are is basically just powers of 2. So the first thing is a prep phase. It's a loop which iterates at maximum, at most 7 or 8. I'm not sure. I think it's 8 times. And what it does is I make use of the stack, and I push my denominator to the stack, onto the stack, shifted by all possible powers of magnitude or orders of magnitude. So for example, if my denominator was 101, right, then what's going to happen on the stack is, my magnitude starts at 1. So what I do is I push a 1 on the stack, and then I push a 101. So this is my denominator, right? This is the first thing that happens. I just keep track of denominator and denominator previous. We'll talk about that later. And the next thing that happens is I shift my denominator by 1, right? So this is essentially multiplication by 2 is a shift left by 1, right? And the same thing happens to the magnitude, right? So we had a 1, now we have a 10. And we iterate, and we push this to stack again. So now our stack looks like this. And then the same thing happens. So we push 100. Well, it's not 100, it's 100, really. And then this number, and so on and so forth, until we end up, until either we have overflow in the denominator, and this is a problem. Basically, we don't want overflow. Not going to go into the details. Or until our denominator gets too large, right? So if, for example, we're dividing 11, or I don't know, something like this, by 101, we can fit this in there. We can fit this in here, but we cannot fit this in there. So we don't need to go further than this, right? We don't even need this really. If this is the number we're dividing, if this is our numerator, right? So this is our the state of the stack, and bear with me, hopefully it'll make even more sense later. So this is the state of our stack. We have magnitudes, and the denominator shifted by each magnitude. And now comes the actual loop of trying to come up with the answer. And what the loop does is, at every iteration, it pops these two things from stack. So we start at the largest magnitude shift of the denominator, and we try to subtract this from our numerator. So, right, the idea is the same. We're still subtracting from the numerator, except what we're subtracting is not the denominator, the raw denominator, but we're subtracting the denominator multiplied by some value, right? So, if I know that, and this is what happens, right? We do a comparison. If I know that my denominator fits into my remainder, right? This shifted denominator fits into the remainder, then I know that, first of all, I can subtract it. That's what I do. And second of all, I know that the original denominator fits this many times into my numerator. So I do quotient plus magnitude plus this many times. And then I restart and I pop again and I go to the smaller value. Again, I'm not gonna go into all the details of how this works and the exact properties of div mods that make this efficient and possible. But this is hopefully my brief explanation is understandable. If it isn't, again, let me know. I can make a much longer video with much more detailed formulas for this. Oh, and by the way, I fixed my freezes in the meantime as well. This did cost me Excalibur, so now we have a weird bar up top, because this is an actual web app, but whatever. The whiteboard is still the same. Okay, so hopefully this algorithm is understandable, and actually you can see that at most, since we are going to stop once we overflow or we get too large, at most we're gonna have 8 shifts, right? Or 7, depends on how you want to count it. So this is gonna be at most 8 iterations, and then since we're popping from stack, we will have a single iteration of this loop for every prep iteration, right? Which, by the way, I detect the end of the poppage when I reach magnitude of 1, so this number. Which means that we're gonna have 8 of these and 8 of these at most, and it's gonna be 16 iteration stops, which is much better than 255 in the 255 divided by 1 case. And overall, I can't be bothered to actually, yeah, like there's a lot of weirdness with the fact that these numbers are bounded. We're working with finite numbers, so the complexity of this algorithm is really going to be O of 1, I'm pretty sure, strictly speaking. Just because we don't have arbitrarily large numbers, or even usefully large numbers. But slightly generalized, this is going to be logarithmic complexity versus linear, or I think this is this is m log n, and that would be mn, I think. And honestly, I can't be bothered to actually calculate it. Or to actually reason about it. So this is much more efficient. And if we take a look, let's try to compare this. So actually, let's use Christopher's solution, Christopher LML, as our original. So we have a tick score of 1025, right? And this here thing, long division based, is noticeably faster, 10 times faster, 108 ticks, right? Well, something along the lines of 10 times, in the order of magnitude of 10. So that's the first thing I did. And in fact, this algorithm is also very good for another reason. Now, you might remember, again, let's run this, that last time when we complete this level, we got all these elements. Divide, divide, divide. So now in math, we have a divide gate, pretty much. And I was unhappy about that. The problem is, what I did is I implemented an algorithm which takes multiple ticks to perform division, right? And it costs an ungodly amount of everything, you know, gate score of 2776 and multiple ticks and everything, and a huge delay. While what I received is a completely different element. It's a division that has a fairly low gate cost and a fairly low delay score. And most importantly, it works in one tick, right? So I can pipe any two numbers into here, and I will get a quotient and the remainder in the same tick. And I was unhappy about that. I do not want the game to give me anything for free, and I want to understand on a deep level every part of my architecture, which, by the way, you may notice that the architecture now looks quite different, but we'll get to that later. Right, so I set out to implement my own division. my own one tick division gate or custom component. And long story short, based on this algorithm, I succeeded. And let's take a look at it. Don't look here. This was a failed attempt at a weird thing. So let's take a look. I don't know. Okay, let me try to explain this. So this is the original solution I came up with. It's ungodly in terms of score and everything, but I think it might be the simplest. So what happens here is, first of all, we have this part, which these small things are shift left by n. So this is shift left by 1, shift left by 2, shift left by 3. And basically this corresponds to my stack. I have my input, I have my magnitude, and they're both shifted by 0, by 1, by 2, and by everything. Now, these switches, again, I'm not gonna go into all the details of how exactly this works, but these switches encode checks for overflow so that I don't get junk results up here, because overflow, again, is a problem. Not gonna go into the details. So this basically is my stack. And now what happens is I have my numerator, and these are all iterations, essentially, of the second loop of my algorithm. So what I do is I get my numerator, I get my shifted denominator, right? And this is a check for the fact that the shifted denominator fits into my numerator, right? So this is less than or equal, less than or equal. And if it is, then it's allowed through. And what happens is I subtract it from my numerator, right? I subtract it, and that's my new remainder. And then the same thing happens on the second iteration. And again, it gets subtracted, and it gets subtracted, and it gets subtracted if it fits at each step. So once I've subtracted everything, that's my remainder. This is my remainder. And in order to get the quotient, what I can do is I have my magnitudes again. This is my shifted magnitude line. And I let the magnitudes through if subtraction happened, right? So if I subtracted, then it means that this magnitude of denominator fits. And if it fits, then it comes, it joins the answer, and I need to add them together. But because of how they are magnitudes and they're just one and a bunch of zeros, I don't actually need the full addition, and it's sufficient to do ORs. So this was the first iteration. This resembles the original algorithm most closely. But that's not the final solution. It's very expensive and very inefficient. So the next thing I did was this. This is already much better. And this is still using all the base gates. And it's essentially the same. It's all the same idea. I still have this part, which is my stack, essentially. I have shifted denominators and shifted magnitude, except magnitude is now 1 bit. Because, again, you don't need to encode 1 bit and a bunch of zeros with a whole byte and have full byte switches. And then, again, the same thing kind of happens. I check if the thing fits, and I subtract it, and then it goes down, down, down. So this is the loop. But there's a couple of interesting improvements here, which will be relevant for other parts. So I will go into a bit more detail. So the first thing you might notice is the fact that there is no less than or equal comparison here, right? So just to remind you, over here, before the adder, we have a whole hulking huge contraption performing comparison, saying less than or equal. Right? And this is important because we need to know whether the shifted thing fits into the numerator. But here, it's seemingly absent. Well, it is in fact not absent, and it's just implicitly encoded in the adder. This is a regular adder, you might recognize. And the yellow line does, in fact, check for less than or equal. So this has to do with how subtraction works. In hardware, we kind of don't have signed numbers in a way. Yes, of course, we can treat them as anything, but all we have is bits, of course. And really the way 2's complement works, and I don't know, I might put, yeah, let me just put a card up here for an older video I made about the properties of 2's complement, if you're interested or have forgotten. The way 2's complement works is, in order to perform subtraction, essentially what we do is we make use of overflow. So, for example, in order to subtract 1, what we really do is we add 255. In order to subtract 2, we add 254. In order to subtract 3, we add 253. And so on and so forth. And that's how subtraction is really implemented under the hood. And this is actually a very useful property of subtraction, especially considering the fact that we have an overflow pin in the adder. We have carry out, and carry out means that we have overflow. So now, the final thing to understand is, in order to perform a correct subtraction, right, a subtraction that does not overflow and does in fact put us below our original number, right, so 15 minus 1 should be smaller than 15, or 15 minus x should be smaller than 15. In order for that to actually work, we need overflow to happen. We need to go, in our addition, we need to go over the final line, over 255, and wrap back around to the start, to become smaller than what we were. So we were here, if this is a number line, we were here, we need to go this way, over the line, and we need to end up here. So in order for subtraction to work correctly, or in other words, in order for the thing subtracted to fit into the thing it's subtracted from, we need overflow to happen, which means we need this thing to be, I mean, on or off. We can use this to indicate overflow. I'm not going to go into the details of how exactly this works. And that's what I make use of here. So instead of having a huge contraption checking overflow separately, I just perform addition, and based on whether my addition overflowed or not, I can make a decision on whether this addition was in fact legitimate, if the thing subtracted fit. So that's the first thing. And the second thing is, you might notice that there's no neg element here, right? Again, just to take a look at the original. Over here, in order to do subtraction, what we do is we take the original value and we add to it the negated value. While in my other thing, we don't have negation, and instead we have two nots. This is an interesting property of addition, which, curiously enough, I was able to come up with using purely symbolic computation or symbolic reasoning. So what we need to do is we need a minus b, right? Now we may recall that minus x in bits equals not x plus 1, correct? This is how negation works. And this is actually how negation is implemented. So now we can write here a minus b. Let's say a minus b is equal to minus b minus a, right? We can now substitute minus a with this. So we'll have minus b plus not a plus 1, correct? Which means that, let's take the 1 out of these parentheses. We'll have minus b plus not a minus 1, correct? And now we can make use of this formula again for this minus. We can say that this thing is equal to not b plus not a plus 1, correct? And then this -1 is still there. And you can see a very neat property here. +1 and -1 cancel out, so we have not b plus not a. And this is exactly what you see in the schematic. Oops, that's not what I actually wanted to do. This is what you can see here. We have one of the inputs knotted, and we have the output knotted, and that's it. Not b plus not. And this is actually cheaper, because a not is just 8 gate score, while a negation is kind of expensive, because it has a ++ operator inside it. Right? So negation is 36. So we are saving a bunch on each of these. So that's cool. Again, hopefully this is somewhat understandable. I've already gone for 25 minutes. And haven't even started. So this is a solution which just uses basic components, and it still has a gate score that's worse than the division we got. And I was not happy about that. Right, this has 848 plus 674, while here we have, well, over 1,000 plus 700. But what we see in front of us can be improved quite a bit by unfolding things and making specialized custom components. And that's what I did. Again, I'm not gonna go too much into the detail of it, but this is my final solution, and it uses a bunch of custom components. You can see the gate score and the delay score are now much better than what we got for free. I'm really proud of this. In fact, this is probably the most interesting and complicated thing I've done in Turing Complete. It's kind of a shame I'm speeding through the explanation of it so much. But again, I've done this so many times now. I'm sorry. Yeah, so what happens here is we have a few custom components, and pretty much all they are is they are components making use of the fact that the input at each point is shifted. So for example, at the very last step, we know that the input is already shifted by 7. So we know that the first 7 bits are zeros, right? So we have 0, 0, 0, 0, 1 at best, at most. Which means, as we've learned in the specialized adder episode extravaganza, which means the components can be reduced based on the knowledge of some of the bits. So here I know that these are zeros, which means I don't need full adders for them. I know that I'm adding 0, and I can just use a, well, in this case, free component, which adds 0, aka does nothing. So yeah, and this is a pretty major reduction overall. The same thing goes for switches. So for example, here we know that the thing is shifted by 7, and it's switched. In the original, it was switched using a full switch, but here, all that really needs to be switched is this, and these are all just off, right? They are nothing. They are not connected. So that's that, and now we have a cool new fancy div mod. I think I've already included it in my advanced AALU. Yep, here it is. The div mod is in the advanced AALU. Yeah, that's about it. There's not much to say about it. I don't pipe out the remainder, I only pipe out the quotient. This is also an issue for multiplication where I discard an output, but whatever, for now, I guess. What else did I... Yeah, and I added it to my instructions. Whereas, yeah, now we have a div assembly code over here. So we now have fully functional custom 1-bit or 1-tick efficient gate score cheap division operator. And it works. And in fact, what I did to make sure it works is I made use of the unit test provided to me by the game. And I plopped my custom component into this highly specialized thing I called LongDiv mod, which just completes the divide level using the direct thing. So this is kind of our clock, right? We know that we'll take 3 ticks or 2 ticks, I don't know. We have some delays here and there, and we just pipe the input into the div mod, and we pipe it into the output as necessary. So this works. This again improves our tick score by 30 times. Because we just solve everything in actually constant time. So now the score on this level is really efficient, really good. Another thing, I promise I didn't do this to optimize my score. I did this actually to check whether div mod worked. I wanted to make sure. And once I did that, I realized that this is a good improvement for the score, and I decided, well, I might as well go back to one of the previous levels, which was, I think, XOR. Yeah. The same thing, we were asked to implement XOR using leg, but what you can do is you can just plop an XOR here with a highly customized circuit, and again, this is going to be an incredibly efficient solution for the level, with a gate score of 33 instead of 2000. So that's another thing, another minor thing I did. Alright, so now let's say we're done with div mod, and let's take a look at, as promised, some ideas for other parts of the architecture which I got from working on div mod. The first thing would be, if we take a look back at, I'm just gonna explain the history of it a little bit. If we take a look back at the original div mod, when I was trying to optimize this, I went about optimizing this part, right? So I was really unhappy with the fact that less than or equal is 2 full operators with an OR, and it was just weird. So before I discovered the overflow trick, I tried to do something about these. And what I realized, if we go into... Wow, where I don't even have it anymore. Yeah, I'm sorry. Yeah, I'm sorry. The thing is, I destructively changed this, and I don't have the schematic anymore. I cannot show it, so I looked it up on YouTube in the older video. So this is my old conditions block, and again, we're talking about less than or equal, and of course less than and equal both exist in the conditions block, and this is what I used to have. So the right part is going to be the less than check, right, from a separate less than implementation. And then I kind of reuse these XORs. These are XORs, by the way. Again, sorry for the quality and everything. These are XORs, and I reuse them for both less than, and up here goes an EQ element with these ORs. And I set out to try to somehow maybe optimize it and improve this setup. And I did find a very interesting optimization, which I think is very cool. So, long story short, this equality is not necessary at all. A separate check for equality, if we already have a less than check, a separate check for equality is not necessary. Here's why. This sequence, this part of the circuit encodes comparison byte by byte, right? So in order to perform, bit by bit, In order to perform a comparison of two binary numbers, what we do is we start at the largest bit, which is down below. We check if they're different, and if they're different, the larger one belongs to the larger number, right? Basically. But if they are equal, then we move on to the next bit, and we check that. And that's what's encoded by this red and this purple line, right? Or pink or purple, whatever you want to call it. So if our bits are equal, we pass control over to the next comparison. Then the next comparison does the same thing. If they're different, then we're done comparing and we know the answer. But if they are still equal, then we need to pass control higher. And so on and so forth. And all I really needed to do is we can switch to the actual schematic with the solution now. Let's take a look in here. All I really needed to do is extend this equals line up by 1, which meant that we have compared all of these bits, and if we're still passing control up, then this means that all of the bits were equal. So none of these ORs and none of this vertical stuff was necessary at all. And equality is already kind of checked within less than. So what I did is I implemented what I called fused unsigned less than EQ element, which doesn't output a less than or EQ. It doesn't have a single output. Instead, we have both things as our results. We have an EQ and unsigned less than. We output them separately. And then from them, this is my new ACOND. From them, we can use the decoder, setup. It's basically the same. And we can infer all our other conditions. Greater than, less than, greater than or equal, not equal. Everything can be inferred from these two. So that is also an interesting improvement, which came from DivMod. Another thing I don't remember if I've mentioned, sorry if I'm repeating myself, but I also added an optimization for addition in the AALU. It's this right here. I'm still not fully happy with this, although I'm not entirely sure if there is an improvement to this that's gonna be major. But one other thing, just again to remind you, since we know that minus x is not x plus 1, in order to perform subtraction, what I used to have is I used to have a negation here, and it used the mux for whether we want to subtract or add, and pipe that into the adder. Now, instead of the negation, we have a not, and if we actually need to subtract, not is cheaper than negation. If we actually need to subtract, the plus 1 comes from the carry in here, which I think is a bit of a clever solution to that problem. So that's another thing. Now, a whole other train of thought spawned by division was a train of thought about improved specialized adders. So again, just to remind you, in order to get a good score on my div, I used specialized adders, which were an instant of my custom 1-bit constant adders. And since I got to thinking about those, that reminded me of my plus plus and minus minus, and my plus plus and minus minus reminded me of my stack. So first of all, a small thing I did was I just implemented the plus plus and minus minus in terms of these specialized small adders. Right, so they're now the same interface, the exact same thing, except with different components. But a more interesting part of this is the fact that I still had an unsolved issue in my stack. There was an issue of whether or not I was going to allow popping and pushing to the stack at the same time, right? So we have a pop and a push. Man, these are now... Again, this is so different now that it's kind of difficult to explain. But we have two separate inputs for pop and push. So pop and push are not mutually exclusive, and in fact we can have neither. We can have neither pop nor push, and theoretically we could have both pop and push. And in my original design, I didn't consider it at all. I just decided that no, this is not going to be an operation that's allowed. And at one point I even had a test for it to short circuit if that happened. But I've been thinking about this, and I realized that, in fact, pushing and popping, goodness, popping and pushing at the same time can be a reasonable operation. If we have something on top of my stack, or on top of our stack, so for example, if the top of our stack is X, and what we want to do is we want to change X in place. So for example, we want to increment X by 1, right? So what we would need to do is we would need to pop X, add 1 to X, and then push X, right? Well, push the X plus 1. And this seems like a reasonable operation to perform in one tick. So we pop, increment, push. And this is how I ended up implementing my stack, or re-implementing the logic of the stack anew. Is I now allow both pushing and popping at the same time, and what happens is the pop happens first, and then the push happens. So long story short, all this meant is I used to have an OR to enable changing my address, right? So the address would change every time we were popping or pushing. Now the address changes if only one of those things happens, right? Where's the XOR? Okay, just do Control Z. So if we're only popping, then we need to decrement. If we're only pushing, we need to increment. And if we're doing nothing, or if we're doing both, then the address does not change anymore. So that's what's encoded by this XOR. And, well, I'm not gonna go into the details again, but I rewired this all slightly just to make sure that in case we're popping or pushing exclusively, it stays the same. But if we're popping and pushing in the same tick, then it operates as I described. So the output will be what was there under our stack pointer, and what's going to be saved is saved instead of what was there in place. So that's a change to my stack. And yeah, I also made it into stackgister, so I now have two pop enablers, which will bring my pop to 1 or 2, you know, just to allow this setup with the light and dark blue wires, which is standard for everything I have. So that's the new stack. And probably the final thing was the instruction address register. Again, since I was at the topic of constant additions, I also implemented a +4. And a +4 is cheaper than a +1. So a counter, wherever that is, come on. Yeah, an 8-bit counter, which always increments by 4. Oops. is in fact cheaper than a counter that always increments by 1. So this kind of setup, this is a counter, just in place. This is cheaper than what we used to have, except, unfortunately, I did implement it as a custom... Come on. I did implement it as a custom component, so let's take a look here. Leg, IAR, instruction address register, so it's the same thing, right? Just a loop that's incrementing by 4 and can be overwritten by an input. If I do this, and if I plop it into here, which... Should I try to do that now? I mean... Man, it's kind of gonna be a pain. Okay, I'll do that because I want to display, I want to show it. So here it is. Again, this is the custom component instruction address register. And it invariably causes a short circuit, which, first of all, fair enough. Obviously, a clock, a counter will be self-referential. This is the most important self-referential part of a computer, if you ask me. But the thing is, it's not self-referential in a bad way, and I'm not sure why the game believes there is a short circuit here, because there is a delay, first of all, between the things that would be problematic, right? Whatever comes in before it goes out, right? So this is the go out line. Before it ever goes out, it needs to go through a delay. So that's never a problem. And what's even worse is the short circuit is between these wires, right? So it's between the constantly on output that's piped back into the program. So this is the program counter, instruction address register, instruction address. And for some reason, these two, either one of them, causes a short circuit, even though it has no influence on the constantly on output, right? So this and this conflicts with this, if we are to believe the game. So I'm not sure why that happens. My guess is it's not clever enough to look inside the thing. And instead what it makes use of, or normally what it uses, is these square pins, right? We did have an explanation of square pins in the manual, wherever that was. Not circular. This, yeah. The exception to this are square pins that do not influence the output in the same tick. So that's what we have in the delay line. They can therefore not cause circular dependencies. So I think what the game wants from me is to put square pins on here. But I don't understand how I could do that. There's nothing I can do here. It seems to have inferred square pins for this somehow, because they're connected to the 8-bit delay line, I guess. But for these ones, they aren't square, and yeah, I don't know. I could connect them to a delay, but that would be wrong, right? I need it to be propagated immediately. So I'm not sure what to do, and yeah, what I ended up with for now is I just... Oh, come on. Please tell me undo works. Undo doesn't work. Okay, let me put it back. Yeah, so what I ended up with is just unfolding the exact same thing and plopping it into here. I guess that works, which it does. It does not cause a circular dependency, which tells me that I shouldn't have a problem. So if you know how to fix this, please do let me know. I would not I do not like having this here, and I would prefer a neat little custom instruction address register. Yeah, and another thing I tried, that was a spoiler which I flashed for a moment, was wrapping input and output in a crazy component like wherever that would be. This IO wrap. And the idea would be I would have these inside with come on, with things just connected to them directly. And then this would have the classic standard register interface. So I would have my light blue wire here, then green wires here, you know, and light blue output here, and dark blue here and here, because that is essentially what I have. But again, as you can see, it's counting a circular dependency where there isn't none, isn't any. So yeah, again, not sure what's up with this. Can't do anything. And do let me know if this can be somehow incorporated. I think that might be it. Yeah, that's about it. And I'm not gonna go for the next levels in this video. It's already long enough, even though I tried to rush through all of my explanations as quickly as I could. I guess one more thing I could address is Yotanido's comment to the level where I implemented call and return instructions, air quotes, which was wherever that was, push pop functions, I think. Yeah, add call and read instructions. So what Yotanido is suggesting, and it's an enticing prospect, is the fact that call and read should actually be implemented as hardware things, so actual wires, so that they happen in one tick and I have separate specialized instructions for them. While what I did is I implemented them as multiple instructions of my existing architecture. I am still not decided on what to do here. Yotanido makes a very compelling case that that's how actual hardware works. By that, I mean Yotanido's setup with a hardware instruction. But I do not see a good way to do that without breaking my current design in weird ways. I'm not sure where I would put these wires, where I would put the thing in the instruction. Do I use bit 16 or something? Will I need, you know, yellow wires running all over here into my instruction register, and then some random adder adding 4 to it to save something into here? You know, there's a lot of weirdness which I feel would be involved in adding these things as actual hardware instructions. And the only gain I'm gonna get from it is I'm gonna save on one instruction. So right now my call is 2 instructions, right? I have put to stack, so remember where to jump, back, and then jump, while my return is literally a single instruction, mov stack IAR. So I am not yet entirely convinced that this is an idea I will like in my architecture, but I'll give it more thought still. I will just idly try to come up with how that would be implemented and how that could be neat, how that could be made neat. But for now, I think I'm gonna stick with my setup, and we'll see how that goes.